So we're here to talk a little bit about Hydra, which is a BMC with an integrated root of trust. My name is Bryan Kelly. I'm a security architect at Microsoft. And joining me is Dan Morav, the Chief of Security Technology at Nuvoton. So the agenda we have on this for the slides today is just the current state of root of trust technology, platform root of trust technology today, the motivation for Hydra and integrating the root of trust into the BMC, quick tour of the hardware and software architecture, some of the scenarios it enables for the BMC, and some of the standardization efforts that we've already seen and are available out on the show floor with DCSCM and so on. So the current state on root of trust technology, I think in 2016, we come out with a discrete root of trust to provide the root of trust functionality. The industry is very fragmented on the implementation of security at the time. And then there's many solutions that were out for a discrete root of trust on a motherboard. We talked with Kirkland, or we heard talks on Kirkland earlier today around some of the challenges that are presented with discrete solutions. But the functionality that's ultimately covered is the root of trust for update, which we talked about in admissible architectures, is the RTRec, and the RTU, and then the RTRec, which was the root of trust for recovery for both BMC and the when I say host for the CPU. Another functionality, key functionality that was captured was aggregation of all components in the system and measurements of all components in the system together into a root of trust solution, and what could aggregate those measurements or have access to acquire measurements from devices in an out-of-band fashion. Since 2016, there's been some standardization, I think, in open compute, certainly around the specifications that have been published, or guidelines that have been published for secure boot, attestation, and recovery. We got in there today. The admissible architectures is something we've spoken about last year on how the systems come together, the roles of RTM, RTU, and RTRec. There's more discussion happening right now on standardization around ROT APIs and what we should expect to acquire this information. So ultimately, the motivation for going down a path of, hey, let's integrate a root of trust into the BMC is very similar to the discussion earlier on Project Kirkland and the display, the demo that's out at Intel's booth on Kirkland. Is like, as Jeff mentioned in the talk around Project Kirkland, with DCSCM, it's becoming easier to interpose between the CPU and the root of trust and the TPM. Also on there is modules. You saw on the DCSCM, the root of trust was modular. It was a modular that was plugged down. How do you know that hasn't been replaced or interposed in? So to establish a flow, a secure binding between that, the BMC and any external root of trust requires that the BMC have security properties that enable it. So very similar to the talks earlier on Calyptra, and about having a root of trust inside in devices is important to be able to anchor trust in that device and then establish some level of security out to other components and secure those interconnects. Another motivation was externally with root of trust and taking measurements on flash chips. You get a certain amount of measurement. You get measurement, of course, of firmware, but configuration, like the device configuration, how it's set up with OTP fuses, what lifecycle state is it in, is debug enabled on the device. Like, these are typically internal properties in the device that are equally as important as the measurement of firmware. So we want to be able to capture those and extend that coverage The other functionalities were, of course, the root of trust for recovery. How do we know that's reliable and in a healthy state? And the root of trust for update. How do we know that's reliable and in a healthy state? And then to be able to get something that we call single pass attestation, which is not having to query a lot of different devices in a system to get the state of a system or the health, to still have that top level measurement that we can understand the state of a system. Another one was enabling new scenarios for the BMC runtime itself. As we see BMCs getting more sophisticated, and I talked about hot patching a little earlier. It's like, what attests hot patching? Like when a device boots, and it boots with a static firmware and static configuration, if that changes at runtime, what mechanisms have we got to know these changes occurred? And by having that root of trust in the BMC and monitoring the runtime, it gave us new capability that wasn't there before. And then another problem that we found with having everything discrete or remote was the interconnects. The SPI interconnect is not really fast. So if we wanted to offload or perform some cryptography, we could never really exercise the full potential of the cryptographic engine because the limiting factor was the bus speed. And by integrating the root of trust, we got we were able to maximize the performance of the I/O and then, of the cryptography. So with that, I'm going to hand over to Dan and let Dan talk about the architecture for Hydra.
And more of the technical dive into details. I hope it will not be too technical or too deep. So this is the architecture we came up with and implemented to achieve or address the motivation and the goals Bryan mentioned. The size here is not proportional to the actual, but to the discussion here. So the first one is the BMC application processor itself, which has also trust zone running under it. We'll address the usage of that later. It is running for BMC. It would be running the OpenBMC application and functionality. We have the root of trust security subsystem, which is a self-contained. It has all the internal components and modules to be able to provide the relevant functionality. We call it TIP, the Trusted Integrated Processor. It would have all the crypto engines and capabilities inside. It would have its own required or mandatory peripherals, such as I2C, UART, GPIO, SPI, and so on, to interface with the required peripherals of the system or the device. It would have its own processor, of course, ROM memory, internal memory, and so on, and its own internal fuse box on the OTP. It would use the interconnect fabric, which we have on the bus, to well manage all the access to all peripherals and memory sections, and it would configure and use that to manage which model internally of the BMC or peripherals can access which other models or interfaces or RAM sections which can be locked to the TIP usage or control and versus the application BMC processor. The whole communication, fully isolated, so the whole communication is using the mailbox to interface and to provide services to the BMC. Last and probably least is the real-time I/O task offload coprocessor that would be dealing mostly with peripherals of which require high attention and high workload and spare that from the main processor from dealing with. Next, I would like to go through the secure boot sequence of the whole SoC. So first, as in every secure device, power on reset, the TIP would be booting from ROM and running the ROM code. It would use DICE to load, verify, and then execute the dice layer 0, measure that, and followed by dice layer 1, which would be running the Cerberus. The tip will be loading the BMC boot block into BMC RAM and allow that to boot from that. It will use that code to initialize all peripherals and DDR memory to be able to load the rest of the code. And when the RAM is initiated, it would load the ATF and the U-boot. Following, reset of the BMC core and execution of the measured and verified firmware up to the U-boot. That one would be loading, verifying, and executing the Linux and file system, followed by the open BMC application we mentioned. It will be also loading, verifying, and executing or releasing from reset the real-time coprocessor to do that work, to do its own work. The services provided by the tip to the BMC and by the BMC to the system would include, as mentioned, the secure provisioning in manufacturing, starting from device manufacturing in our manufacturing, to endorse the device manufacturing endorsement. We would use this static key, which would not change. That would not be part of the dice boot, so it would not change with the layer 0 changes if they are required, and that would allow a static, unique identity, which will be the same and will not change through running different firmwares, whether in manufacturing firmware or later on if layer 0 need to be patched in the field. It will have a separate dice device ID with the classic and the specifics of the dice with full-blown. The DME would be used to endorse the dice device identity, and that would allow later binding and endorsing or applying a dice device ID certificate through whatever CA is used by verifying that it is indeed a genuine device which is familiar and known, even if the firmware layer 0 is changes. The dice boot is following the OCP secure boot data structures and flows, so same and following all the requirements. The measurements, as Bryan mentioned, include the configuration of the device, the tip itself configuration, and the BMC configuration as well can be used as part of the measurements and will be used to derive the dice keys or the later on measurements reported during the attestation process. That would include the lifecycle configuration. That could be also the interface fabric mentioned earlier, which is used. That's part of the configuration, which can be also measured and used as part of the measurements. With respect to firmware resiliency, we have a hardware model to monitor dynamically the access to the flash, whether it's the flash device used for storing data or information for the tip itself or the BMC. We can monitor it like, imagine a spy firewall. So we could monitor and allow access to specific commands of the spy or specific reads or writes to specific areas, so we can fully monitor that during runtime. Also for tip firmware or data, BMC data and firmware, and so also for the host BIOS firmware as well. We do that on the fly and dynamically during runtime. And also, as Bryan mentioned, also the secure update and recovery for all the chain, starting from the RoT, BMC, real-time coprocessor, and the host BIOS firmware. With respect to applications and secure application introduced and provided, we'll discuss mainly two of them. One is the firmware TPM running under the trust zone and using the RoT to generate and certify the endorsement key of that firmware TPM running on the BMC side. And sorry. And as Bryan also mentioned, the Linux kernel runtime measurements that would allow to measure configuration, the code itself, or data, or whatever is on the BMC side, whatever is selected or chosen to be monitored during the execution. So the services and the boot flow mentioned earlier allows us to build a certificate chain starting from Rome up to the firmware TPM running in the BMC. I'll go briefly over that chain. We first have the DME I mentioned earlier, which is static, generated inside the device, and the key is generated. And in the ROM code, it's never exposed to the dice layer 0, but the certificate can be endorsed by the manufacturer, CA. The DME key is used to sign the configuration and the dice identity public key. So we can tell and verify that the device is indeed in correct state and it's genuine device identified. So the platform manufacturer or owner, whoever is running the firmware, can verify that and generate a certificate for that device identity key whenever required. The dice device ID would be used in a standard dice form and application to certify the alias key running in layer 1 under Cerberus, which will generate and certify the firmware endorsement key, which will be passed to the firmware TPM running under the BMC. Just a short recap. So we have the measurements verified up to the dice layer 1 on the tip side, and all the measurements it does up to that layer, including the measurements it's doing to the boot block, ATF, and U-boot, are all registered and kept in the tip PCR, Platform Configuration Register. And all the measurements done from the U-boot on of the Linux file system, configuration of that, and the OpenBMC, these one would be recorded and registered in the firmware TPM PCR. That would allow us to later on do attestation using standard TCG library and tools to do attestation of the through the OpenBMC application and down to the firmware TPM EK. The lifespan of the EK can be, the policy can be managed by the RoT. Can be defined how frequently that would be changed or endorsed, and what is the validity of that certificate and how frequent that need to be refreshed. Yeah, so the last bullet and the last point is really that using standard TCG libraries and tools allows you to perform and execute the attestation, and nothing special need to be renewed or written or implemented for that. And Bryan, please follow up on how attestation is performed.
Yeah. So this is a really high-level view of how the attestation is performed on the BMC. So with that root of trust internal to the BMC and exposing, it's a combination of the root of trust and also it uses trust zone a lot for the FTBM stack, which is kind of big, and so we don't put that whole stack in the root of trust. Instead, the TPM APIs run in the trust zone, but they call down through a mailbox interface to the root of trust. The root of trust manages the keys, exposes some crypto engines to the trust zone, which enables it to have some cryptographic operations at higher speed for measuring larger blobs like the Linux kernel and updates to that. Of course, the attestation client can then sit in user land and use the existing TPM TSS stack in Linux. The measurements are stored in Cerberus and in that TPM stack. that are queried by a remote attestation service with an attestation request. That attestation service verifies the measurements, walks the identity back to that Cerberus, that DICE identity, which is then endorsed by that DME. It checks the identity, checks the measurements. If those meet policy, it seals a key to those measurements, which is returned back to the BMC, and then the BMC will pass that sealed blob back into trust zone, which in return passes it back to the Cerberus, and it will use that key for later endorsing the TPM and accessing resources. Just on the ROT firmware stack, we implemented the Cerberus stack, which incidentally was published several years ago, so it's out there for folks to view. We're changing that to allow commits and so on into that stack, so folks that want additional functionality can go take that and modify that stack. It does, of course, the secure boot and attestation, as we mentioned, it follows that. The stack that runs in the BMC is fully open source. Actually, the ROT is a U-boot, ATF, the FTPM, the TSS stack, and it runs OpenBMC. In addition, there is a DCSCM available, and we're in the process right now of contributing that to OCP. So as BOM schematics and Gerber files, if anyone wishes to go and manufacture a DCSCM, that will be made available through OCP. So then, call to action is join the work group. We talk about this stuff all the time. If you don't attend, it's on Tuesdays at 8:30 Pacific. I don't know where that is in the rest of the world, depending on where you are. How is it? Where is it in Israel?
Oh, 6:30
oh, there we
p.m.
Go. 6:30 p.m. in Israel. So also, we have a demo of a Hydra over in the Microsoft booth. And with that, we'll open to questions, if there's any.
Thank you for the wonderful presentation. It was very interesting to me. Do you expect Hydra to act as a platform root of trust or an active root of trust, or both? And if active root of trust is just limited to the host CPU in addition to the BMC, or could scale to more than just those two?
Yeah, that's entirely possible, and those two models are supported. It's entirely possible to do that. BMC typically has tentacles out into every other component in the system. So like it's got your I2Cs if you want to do your SPDM challenges over I2C. It's got PCIe, and it can do it, SPDM over MCTP if the CPU complex supports MCDB bridging. So it is well positioned to send challenges out to the device, either PCIe or I2C, depending on what the other devices have. And then the software stack and what you choose to do on that root of trust, whether you have a discrete and a Hydra or you have only a Hydra, that's really a decision for how you build your DCSCM. But the model is supported.
Okay, just a follow-up on the AC-RoT aspect. You mentioned monitoring. Yes. And so I assume there is monitoring for the host CPU firmware as it is read. So that would put a potential limitation on the scale. How many different devices can I monitor? So is there a count that is supported in terms of monitoring?
Correct. So for the SPI controller that sits behind the BMC and is loading like BIOS firmware from the BMC, yeah, but are you talking about PCIe devices where you might query a PCIe device that has an RTM to get its measurement?
Just a general purpose device where the AC-RoT may not be as much trusted.
Oh yeah, you can load firmware from there's multiple interfaces, eMMC, if you want to actually go go a little faster than SPI, you could use eMMC to store your firmware binaries for other components in the system.
Okay. But in terms of SPI monitoring in particular, is there just one additional interface?
Oh, no, there are several. I don't remember the count of Uri.
Is it 6?
Four?
4.
4.
Thank you.
4 monitoring buses.
Thanks.
Do you plan to move to SPDM from Cerberus?
So Cerberus supports SPDM Lite. Ooh, I don't know where the question is. Here we go. Yeah, so we go with SPDM Lite instead of the full-blown SAC. And similarly with the TPM, we have a smaller subset of the TPM that we leverage. We don't use all scenarios. So we like to go at only the code that's necessary.
So there's been a lot earlier today talking about Project Kirkland. Have you done any tests or any reference implementations of running Hydra with Project Kirkland in kind of the same BMC? Like we're using an external EROT.
So for an external root of trust, yes. For an external TPM, no. But it's the flow is the same. Like the Kirkland flow can apply really over any interconnect. Uses SPDM Lite, kind of like a key exchange, and then from then on you get an encrypted session. But we do believe all interconnects should be secure and confidential, including USB and other interconnects. So we have quite a way to go on some of those standards. PCIe is already there with IDE and TDISP. Now today with Project Kirkland, the other most important link in the system is probably that TPM link, so that's secured. But you're right, links out to IROTs and then USB also needs to be secured.
I would just mention that the Kirkland was mentioned, and the secure link is between the main host CPU and the TPM it's owned, and not the TPM mentioned here, which is running under the BMC and serves the BMC only. So for the for the discrete TPM in the system where the main TPM servicing the main host, you would want only one host, which would be the CPU, and you do not want to intervene or interpose that.
Yeah, the host is different. I was thinking of like, at this point, the BMC is looking like the host architecture. It can have an EROT, have an IROT now. So it's the same flow, and you just substitute host with BMC.
Yeah, but it doesn't, what I think what Dan is saying is it doesn't have an external TPM here. The TPM is all internal on the BMC.
I see your point.
Okay.
Thank you.
So there's no interconnect. And one other thing to mention, there's no LPC to AHB bridge.
Though, not on this one.
Yeah, that's a very important one.
I have a similar question. What was the main motive of using FTPM for Nuvoton than using a standalone component?
It's necessity. You can totally optionally, it's a preference. You can go and use the external TPM. I think the trust zone TPM, like running the trust zone TPM, like why didn't we put that whole stack down in the root of trust? A couple of things is performance. As you go over to SpyLink, you're limited by the performance of QSpy. So if you want to take a lot of verbose measurements of your kernel, then or you're measuring large blocks or blobs, then you get limited with the external TPM on performance. When it's internal, that's like a context switch, so it's super fast.
And another taking advantage is the RoT is creating the EK and generates the certificate for that. Otherwise, if you use a discrete external TPM, you would need some handshake, which may be more heavy, and again, performance heat on that as well.
Thank you. Dan, you mentioned the FTPM is for sort of exclusively for BMC's use. I'm just wondering, is there anything that stops the other measurements if BMC has access to, and if it tries to put in there, is there a real reason why you want to make it exclusive to BMC only?
I think with this architecture, we are since you have to have one host per TPM and one-to-one binding, it will be impossible to use the same TPM for servicing both BMC and host. With respect to measurements, since the BMC is measuring and verifying the BIOS flash anyway, but we don't have a standard secure way to post these measurements and give them to the host TPM.
Yeah, I
To extend
understand
that into
host
the
and
PCR.
BMC need to
Okay.
be separate, but my question is mainly on the other measurements that are accessible to only BMC. So TCG server work group specifies a way to put those measurements into TPM attached to BMC. So
I think what we'll do is follow up on that question. We're getting cut off. And your question too, we'll follow up on.
What happens if you need to patch the FTPM? You need to translate all the secrets to the new version. Do you already plan that flow?
As I said, I'll follow up on your question offline. We've got to allow the next talk. Yeah.
Thank you.